Today I will talk about mainly this paper by Blackboard. It's SUSY's ladder. This is work with matrix is exactly at the diphoton time, so possibly not so many people focus on notice this paper. I needed to take many opportunity to advertise it. And basically this is about the model building and the cosmology. The second part, if I have time, I will talk about our future. In the future, Collider can we probe the split SUSY in an indirect way. So let's start. Start from why we talk about split SUSY, why we like it. As we all know that LHC discovered Higgs, and it's too light. If you want to go to BSM, you need a fine tuning, or you can guide it by the naturalists, or you can just accept the fine tuning. Let's just accept the fine tuning. What we have, one option is split SUSY, and after we get rid of everything, what's the new feature we will have? First, it's easy for model building, like we know like anomaly mediation, SUSY breaking, or some gauge mediation. They can give you the hierarchy like there's separation between the scalar mass and the gaugino mass. They're separated by one loop order. This is just to draw it here. This is scalar mass. This is the gaugino mass. This is T possibly 100 GeV, and this is maybe something. And the other thing is like they can give us the very precise Higgs mass prediction after you include the tree level and the one loop and the loops. You can have the Higgs mass prediction quite well. And you get the correct 125 GeV. The third one, let's talk about phenomenology. And if you have these two things, what's the scale? What's the natural scale should be? One is you have flavor constraints. Flavor constraints. You put your mass more or less larger than 100 TeV, the scalar mass. So it means that in the future collider even possibly cannot reach this scale. So the other thing is like you want what's the scale for the gaugino? And one thing is that we have WIMP. WIMP is tell us it's TeV, or you have unification. Along TeV. Any questions? Okay, so in the SUSY framework, there's another particle. It's gravitino, and whether we have some phenomenology argument or theoretical argument, what's the mass of the gravitino? This is the question we want to address in this talk. To answer this question, I want to go to the cosmology. So first, let me just go one brief review on the indirect detection search. What's the current status? And we know that we have Fermi-let. That's constraint. You have dwarf constraints, mostly constraint like Vino or Higgsino, that smaller than 300 GeV. And recently we have the HEISS. The HEISS experiment can constrain the high mass Vino. So mostly the Vino parameter space is in tension. Here we assume that 100% of the dark matter is Vino, and also we should assume that the dark matter density profile is NFW. For the Higgsino, right now the constraint is 300 GeV. Larger than that is fine. So the other thing we want to talk about is gravitino. Do we have some hint for gravitino? Let's just draw the mass for the gravitino. I separate them in the 4 region. 1, 2, 3. And the first one, here is the first region. Here is the neutralino. When the gravitational mass is smaller than the neutralino, the gravitational becoming LSP. So region 1. Gravitational becoming LSP. You will see that there was the older neutralino. If it survive after the freeze out, they will decay to the gravitational. So you have this process. Can you see me? just roughly. This process happened in freezing and freeze-out process. Freeze-out means that you finally you end up with the neutralino has the more or less constant comoving density. They will cascade decay to the gravitational. And for the freezing means that before freeze-out, this neutralino will keep decaying gravitational. So all the process in the whole history of the universe, you have the contribution for the gravitational. And let's go back to the very early universe. You have some thermal process even can generate the thermal process. The thermal process will depending on reheating. Can I just move a little bit? So all three processes adding together, usually you tend to overclose the universe. So for light gravitational, the first region, you always overclose the universe. For the second part, let's just divide it. For the second part, I should here the gravitational becoming not LSP. They are decay to the neutralino. So it do depend depending on the mass. It's depending on reheating temperature. There's thermal process will depending on reheating temperature. But for freezing and freeze out, it doesn't depend. Only depending on the mass of the neutralino. The other region is like we want to talk about the gravitational decay. What's the decay rate? So gravitational usually have coupling suppressed by m Planck, amplitude square Planck. Make the dimension correct. You have gravitational mass cube. So let's just then the gravitational will keep decaying, and mostly we are decaying about what's the temperature? It's like 10 MeV. You have if your gravitational mass is 100 TeV. This is the gravitational decaying time is about 10 MeV. When I write 10 MeV, so this gravitational is 100 TeV. So when I write 10 MeV, you should get immediately varied because they have the BVN bond over here. You don't want your gravitational decay have some BVN concern here. Let's say the third region. The decaying temperature is smaller than the neutralino mass or smaller than the freeze-out temperature. This third region is smaller than T freeze-out. When I say freeze-out, it's about the neutralino. So they were changing the thermal process. You already have some dark matter abundance from thermal production. You dump more into the abundance, you get more constraints. So say in another way, you possibly can produce less dark matter abundance from thermal production or freeze-out process. But in order to do that, you need to make cross-section larger. The larger the cross-section, there's more tension with the indirect section or the constraints. So here is like 10 to the 4 or 10 to the 5 TeV. you have dark matter concern. So 2, 3. The fourth region is like the temperature is larger than the freeze-out temperature. So you have a normal freeze-out process. We call it the safe region. This is some. You have many things. Actually, he is very hand-wavy argument. That here you can always solve this problem by other methods. For example, you have low-scale inflation. This is one you don't produce the gravitino, but here we want to say that whether we can build another hierarchy that we are motivated here is the gravitino can be much higher, and how do we do that? So let me go to the.
Can I just ask about the third region? I'm a bit confused. I think I don't quite understand.
Sure.
So here for the freeze-out temperature of the neutrino, so TeV neutrino, so wouldn't that be around 1 TeV divided by 25?
Yeah.
But so what's T3 house? That's the freeze-out temperature of. What's the T3 house?
Oh, is the decaying is the gravitational decay in typical temperature.
Oh, sorry. Okay.
So this will you just make the gravitino larger, you will match this temperature.
Okay,
so we were trying to do model building or something. Can we just get this we call the sequestering scenario? Let me just do some very naive computation first. What's the third one? Heavy gravitino. Let me first do it in just a naive estimation. Gravitino usually related to the supergravity, so let me use the conformal compensator to do that. Q is just you can think of it as just quark. Phi here is a conformal compensator. Because I need using this conformal compensator all the time, let me just say some words about the conformal compensator. This is one way to describe supergravity. One, we know that we want to lift the diffeomorphism to superfeed transformation. When you do that, you will end up with Lagrangian has too many symmetry, like super conformal symmetry, Dalton stuff. You want to compensate this symmetry to make a phi feed. To make a Lagrangian is the same as the OR word. You need a compensator over here. So typically the compensator is have F term depending on the curvature of the ADS space. It's the gravitino mass. So just now you put the F term, you will get immediately F squark mass is more or less the gravitino mass. The other thing is the gaugino mass. The gaugino mass can come in from anomaly mediation. The compensator is not only a trick. It's actually something that's really related to some physics over here. You can write down the gaugino superpotential over here. That's depending on mu. And any cutoff you can rescale by the conformal compensator. When you expand it, you will get something. I think it's maybe 4. Depending on the RG flow coefficient of the gauge feed. When you expand the phi for the F term, you will immediately get the gaugino mass is just one or the just coupling suppression relative to the gravitino mass. So we will end up with this. Seems like if you just naive estimate, your gravitino is here and only one is not away from the scalar mass. So actually, it's well known that we can make here is not the mass term, is actually the F term for the phi field. You can use in the no scale structure. You can use no scale structure to make f phi equal to 0. This was what we should do is the scalar potential. You have the phi deck phi term. Also have linear term. It's called the modulus. And for the superpotential, you add a constant term to make to lift the ADS space to the Fly space. Possibly there's -3 over here. And to make the conformal weight correct, you do the add phi cube over here, and let me conjugate. Yeah. Yeah. But it's really, this is dominant one, right? It's not coming from. Yeah, this is only coming from the F term of the phi. Okay. So here, go back to this no scale structure. The dominance, the key thing is there's linear term. You can just expand the F term for the T field. You do the equation motion for the Ft dagger. You will get immediately the F phi equal to 0. This will suppress a lot of SUSY breaking effect, including the normally mediate effects. This is how it works. It's really in tree level. So the next step, we want, actually, when you add this one, you find that F phi is 0, and you will get possibly, if it's just tree level, no scale structure, you will get the gravitational mass seems 0. And let me see how the quantum correction can change this scenario, whether this hierarchy we built here are stable in the quantum corrections. Or using effect field theory to understand the mass over here. You have we know that we have a gravitational mass pretty heavy. They should have some radiative correction to the mass of the scalar or the mass of the gaugino. What's the correction should be? It's just a scalar feed. This is phi feed. You have gaugino loop. If you have the graviton loop, usually the divergence is like coupling to the force. But here is for non-SUSY, you will get the correction to lambda to the force and suppressed by M Planck. But here the supersymmetry, you suppress the quartic divergence to quadratic. So you compute this suppression, this quantum correction. This will depending on first the coupling, M Planck square. There is some loop effect here, and also depending on the mass of the gravitino. And you have something quadratic divergence plus log term over here. Then the second question is, what's the mass for the gaugino? You still consider this loop. We know gaugino, you need to break the Carrot symmetry. You should put the mass term over here. So the gaugino mass is proportional to the gravitino mass divided by the coupling is by the M Planck suppression coupling, and you get the same suppression like quadratic divergence and log divergence. So if your cutoff scale is smaller than m Planck, you do, let's define the epsilon here. Epsilon is the suppression of the, you have epsilon pretty small, you will get usually the quantum correction for the scalar mass is about epsilon times gravitational mass, and the gauginal mass is epsilon squared times. So this is at least this is the mass should be here, unless there's some interesting cancellation. So here we already say that this is epsilon suppression and this is epsilon suppression. And there's another two scale over here. One is m Planck, the other is cutoff, which defined as epsilon.
Physics should I think about the cutoff?
The cutoff, yeah, good question. It's like the cutoff usually is, you can think of the KK mode from the actual dimension, or even string scale is more or less is smaller than the m Planck. So if you have a large volume scenario, it's okay. Then you have a gap over here. What's the epsilon? What's the scale power here? You do have, because we just go back to the no scale structure. Actually, they give us, if it's in 10D, you can compute the gravitational mass. It's suppressed by epsilon. If it's 5D, it's suppressed by epsilon square. So the next question we want to ask is, we want to do computations. The computation is like, we want to understand how the modulus decay, all the stuff. Let's do computation. And we want to use a gauge. It's developed by Cliff, Francesco, and Jesse. We call it CDT gauge. This is the gauge for conformal compensator. Why we need to do that? Let's just write down because there's a kinetic mixing. If you just focus on this, so the conformal compensator, there's a kinetic mixing between graviton and the modulus. There's a kinetic mixing. Let me just write down this term here again. Why there is a kinetic mixing? Every time you have a phi dag phi, there is a component here proportional to curvature. If it's a curvature, it's a graviton, and you have linear term here, you have kinetic mixing. If you use this one to compute the decay of the modulus, I think you have to resum. It's not a good framework frame to do that, so you need to do rotation. Actually, the CDT gauge is tell us how do we do the rotation. We have some gauge choice. It's just the shift the phi goes to Z is on superfeed plus the F phi theta 10. This gauge choice for the compensator can be understood another way. It's like your Kähler potential is changing, and also your superpotential changing this way. That will not make the supergravity computation different. If you do this change, at the tree level, the supergravity computation should be consistent. So let me write down in the no scale structure, what the phi looks like. is actually depending on the value of the modulus. And also this is superfeed, but the C means that the canonical term is already, the kinetic term is already normal. And here this is the F term I write down as a theta term. So this is only theta square component, F component for the TC. When we expand this linear term, you will find that the theta square term exactly cancel. It's consistent with the Fi equal to 0. When you're adding this back to the Kähler potential, you also find the linear term cancels. There is actually the no-scale structure have one string phenomenon working on this called the large volume scenario. There is there are some interesting cancellations we don't understand. But after you use this gauge, and seems very clear why this happens. Let me just give you one example why this happens. The example I want to give you is modulus decay. This is related to the cosmology. Maybe use another board. Is we want to understand the modulus decay to Higgs signals. Usually, if you don't use modulus no-scale structure, what result you will get? You will get this modulus will decay to Higgs signal and also decay to Higgs. The rate almost equal. So we want understanding the modulus decay to HU, HD, or Higgs signals. Are the rate are the same? It's in the no-scale structure, as I said, the phi is like this. Let me see the phi. The decay rate, you can just come in from this phi dagger, phi times HU HD. There's a term proportional, linear proportional to the TC. When you expanding the phi, you get the linear term at the proportion of the modulus, and also coupling the HU and HD. But here there's some special here. There's no F term over here. If you get F term, we saw the F term, you will see that you can two Kähler multiplied time together. You can think that one Kähler multiplied. So this is just a kinetic term for the T mu, TC dagger, and also partial mu for HU HD. So when you compute this rate, you will find that this rate will proportional to the mass of the modulus. But for the Higgs signal, there is no F term over here, so there is no decay to the Higgs signal. That's the one example I want to give. So finally, let's go to the last point for the SUSY's ladder. It's why you go back to the literature, you find that only 5D have this no-scale structure, and also type 2B 10D supergravity have this no-scale structure. You ask why? The reason, or this is just some simple reason because 5D and 10D are interesting. The things like we starting from some metric. You have the metric is like D equal to D plus N. N is compactified dimension. It goes to D finally. And this is the metric. Let me just write down the answers we will have. This is normal flight or flight space-time. It's plus extra dimension. There is a modulus depending on x. HIM is the metric for the extra dimension, and this is DYL, DYN. After we compactify it, we want to go to a frame. We want to go to a frame that don't have the kinetic term for the L. So you write down the Lagrange after you compactify it. You do Weyl transformation. You want to go to the frame. There's no connection for Elton here. Yeah. Let me just. The alpha is why we want to go to the Lagrange. There's no connection. This is because the node scale structure we just write. Its node scale structure is the same that this is always alpha curvature coupling to a linear term. There's no connection for the others. So let me do the only non-SUSY version. You want to get this term. So what's alpha? Alpha is something depending on some function depending on all the variable d and n here. So the alpha has really some meaning. It's like the volume of the alpha dimension internal space. Then we focus on when the alpha is an integer. So if we restrict all space-time is 4, or space-time is 4, and we find only two solutions for this. This is alpha equal to 1. The other is alpha equal to 4. At alpha equal to 1, this is actual dimension equal to 1. This is actual dimension equal to 6. This seems to give us some hope to tell us why dimension is 10 and why the dimension is 5. Actually, you want to see more explicitly, it should go to the supermultiplet. It's because when you go to supermultiplet, you will find that this T feed has not also have an imaginary part. This is the axion particle is coming from 5 dimension is coming from a mu feed. It's integration, actual dimension. You get axion. This is a 1-form feed. For the type 2b 10 dimension, you have 4-form feed. So the alpha equal to 4. When you integrate it, you get an imaginary part. That's the reason we think let's give us why the 5D and the 10D very special. So let me. Oh, yeah. Thanks. So let me summarize for the SUSY's letter. So first we use a cosmology argument saying that there's sequestering. Sequestering means that the gravity node is pretty heavy and want to build a effect field theory on it. We found that in the tree level you can realize it using the quantum correction. Seems this thing is stable, and we also provide the effective theory framework. Maybe you can make the string phenomenon easy to compute. The last one we have argument why the actual dimension is 6 or 1. That's the first part of the talk. And let me go to the second part. Just.
Can I ask you a question?
Yeah.
From the very beginning, going back to what Gabriel asked, I thought if phi is a conformal compensator, which is to say auxiliary field in supergravity multipliers, then it really can be rescaled away and doesn't give it 3 levels of works of mass. So if phi dagger phi 2 dagger q,
Yeah.
right? From that Taylor potential, I thought you can rescale phi away, and it doesn't give a soft mass. That's the whole. I thought it's the whole basis of anomaly induction.
You can rescale it.
You can do holomorphic field redefinition, and there is no 3 levels of mass.
Sounds correct to me. Let me maybe check offline. Yeah, thanks. Can I just at the same time set up the stuff? How do I? Or maybe you ask. Sorry.
Do you gauge boson scattering into gauginos in exchange for Bragg-Dino?
Yeah.
That amplitude is going to grow with energy, and so you're going to hit a perturbative unitarity limit, which means there's another scale in your problem there, right?
You have sorry, say it again. It's a gauge.
Gauge boson
gauge boolean and go to gaugino and
Yeah.
gravitino.
Yeah.
You exchange by gauge feed.
No, they exchange by gravitino.
It's exchange. Oh, okay.
So this is going to give, the amplitude is going to grow with energy, and so you'll have a unitarity limit as well. So what is the Riemann model? I mean, that means that you can't, in other words, you can't separate the gravitino and the gaugino by too much.
Yeah, but this coupling do have separation of the M Planck, right?
Yeah, there's M Planck in the formula, but where is that scale in your ladder here? Do you have it in there?
I guess it's possibly just lambda. I didn't. You think that it's possibly lower?
It could be, yeah.
It could be lower. I didn't compute it. If it's roughly just dimension estimate, lambda squared is not there's it's the cutoff scale divided by M Planck. You want to hit the unitary bound. It's possibly what's the other scale you can get?
What is gaugino?
Gaugino mass and also it's like combination.
So there's some combination, but anyway, we can discuss.
Yeah, we can discuss this.
Move on.
How do I? How do I turn on a projector? Oh, it's a switch on. Oh. Okay, so the other thing is maybe I don't have enough time. Let's just go quickly and tell you the goal and see what we can see in the future collide. So here's the Higgs mass, and we observe the Higgs mass. The goal of a second project is to figure out what's the underlying mechanism for the Higgs mass, or we ask whether MSM can explain the Higgs mass. It depends on a lot of parameters, but at the tree level and one loop level, it only depending on two things. One is the tangent beta, the other is the scalar mass, or basically it's the stop mass. There is a prediction over here, give the right Higgs mass, and there's band over here because of theoretical uncertainty. We do interested in the region from either theoretical point of view or experimental point of view. We are interested in the region at tangent 2 to 4, and also the region scalar mass is 10 to the 4 to 100,000 TeV. So we choose 4 benchmarks here. There are these two smiling face give you the correct Higgs mass, and these two give you the wrong Higgs mass. Can we use a future collider to figure out the underlying mechanism for Higgs mass? This is the question. The two scale we want to figure out, one is M0, the other is tangent beta. When the scalar is super heavy, your Gruino cannot decay to the stop, but it do appear in the loop. So you have 1 to 2 decay, you have 1 to 3 decay. The 3-body decay is dominant, and this is almost the ratio of these two rates. Right now, you don't need to focus on this. Here's the map for the Gruino versus the scalar mass. Here's the region that stop is pretty light. Then you don't need to search. You can do the direct search, and also when your M0 is larger, your Gruino decay length is longer and longer. You have a lifetime measurement. There's the median zone. Let's say it's also what we interested in the region that scalar mass is 10 to the 4 to 10 to the 6. The white region is the target for the future collider, possibly, if we want to explain the Higgs mass by MSM. And the thing is, we want to indirect measure the M0. You will see that the branch ratio of the decay to the two-body decay will be sensitive to the M0 by the logarithm scale. So we have a hope to search for this in this way. So the goal is just to measure the M0. This one we just choose one benchmark model. It's like Higgsino is in the middle, and you have M2 larger than Higgsino larger than M1. Here, this is the value we have. Gruino is like 2 TeV. I'll just mention one word is that if it's 2 TeV, it means that you have a lot of Gruino produced in the 100 TeV collider, more or less 20 millions. So most of you have gluon fusion to get 2 Gruino. Most of them is 3-body decay. But there's one channel is 2-body plus 3-body, and we want to figure out the vortex here. After we do some study, this is some background versus signal. This is scale for the M0 scale. You will see that the standard amount background and SUSY background are more or less constant. The signal will depending on the scalar mass scale. So using this way, we can figure out what's the M0 mass. The other thing is, if you want to really to solve the mystery of the Higgs mass, the other way is like the other thing we want to probe is tangent beta. Actually, there's many things depending on tangent beta. You have Higgs decay to 2 gamma. If you have chargino in the loop, you will modify it depending on tangent beta. If you have like charge vino decay, it's also depending on tangent beta by the loop effect. But this is all depending on the collider. Can we use the direct detection to search for it? Actually, we do. It's like here is the plot for the spin dependent divided by the spin independent cross section. The spin dependent is more or less Z boson exchange by neutralino to neutralino, and for the spin independent is a Higgs exchange. They both have tangent beta dependence, and also they will separate the sign of the mu. You will see that when the tangent beta 1 to 4, you can get a clear dependence, clear the ratio over here. And we expect in the future, we will see that, this is very optimistic, in the future we will see the spin independent and then push the experiment to see the spin dependent. In this way, we can figure tangent beta. The other method is like go back to this benchmark point. Here to steer the collider whether we have the tangent beta dependence. The benchmark point is still the same, 2 TeV Gruino. And you will generate the, let's say, Z boson fusion. Z boson fusion, you will generate H1 and H2. Why depending on sensitive to tangent beta? This is because, let's go back to tangent beta equal to 1. Your Z will produce the H1 and H2. The parity odd Higgsino will be a mass eigenstate. So it only can decay to Z. Another Higgsino only can decay to Higgs. So in the tangent beta equal to 1, you more or less get a 0 signal. But when you go to larger tangent beta, you break this symmetry, and you get a more and more ZZ channel. And the ZZ channel is easy to search. We only look for Z decay to 2 lepton. So this is basically the search for 4 lepton plus large missing ET. And adding all together, here's the chance we can see in the future collider. If this is the benchmark model, what's the statistics uncertainty here? The gray line is the systematic uncertainty. If we assume that there is a 3 inverse antibody data in the future collider. Okay, let's. Yeah, this is assume. This is a benchmark model. Actually, it means that you possibly need to know it in other places like CEPC. You possibly know roughly the value. Yeah, okay. That's the talk.
More questions to Wei?
Yeah. Oh, they are all prompt decay. Possibly in some region, M0 becoming larger, you get a little bit displaced. I should say that the displace, it's really here. It's 100 micron over here. If it go to lower, it's your decay length becoming much smaller. We just assume that this is a problem. But possibly in some M0, it's close to 1000 TeV, you possibly this already displaced the vortex. Hydron? Yeah, if it's displaced, I guess they possibly get hydron, but this is not the focus on our work. It's what M0? This long lived is just the M0 equal to 10 to the 6. What's 10 to the 6 GeV? It's becoming hydronized. Is it okay? Yeah, I don't know the answer for. Thanks.
Anybody else?
Yeah, this is really heavy, like 10 to the 5 or something, 10 to the 6. Sure. Let's agree. It's a 10 to the 5. It's almost borderline. I think so. 100 TeV. I remember this on top of my hand. It's a possibly 1000 TeV. I remember it's 100 TeV. You think it's 1000 TeV? Okay, it's over here. Yeah, 1000 TeV.
Anybody else? Right, let's thank Wei again.